Okay, welcome back. For this part of the course, I'm going to talk about the Eigenvalue decomposition. The theory part and the relevant application has been explained on the PowerPoints before this lecture. On this one, which I'm just going to use the whiteboard, I have given you an example of a square matrix, which is a 2x2 matrix. It has 2 rows, 2 columns. I'm just going to use the eigenvalue decomposition in order to factorize this matrix into 3 matrices, which they are composed by just the eigenvalues and eigenvectors that we know. On the slides that we talked about, you saw that actually. The matrix A, which is an arbitrary square matrix which is given to you, you can decompose that into 2 matrices. First, you have the matrix of the V, which it's a matrix built from the eigenvectors. You have another matrix, which is a diagonal matrix, which all elements on the diagonals, they are just going to be the eigenvalues from the given matrix A, and also you have the inverse of the eigenvectors that you extracted and made an inference about that from the matrix A. Then, if you are given the matrix A, which is an arbitrary matrix for demonstration here, which is a 2x2 matrix, I'm just going to decompose it into the matrix of the eigenvalues, a diagonal matrix, and the eigenvectors, the inverse of the eigenvector matrix. If the matrix is 2x2, it's going to be a very easy and straightforward path to take. Now, I'm just going to erase it, but as you saw on the PowerPoint slide, in order to start, I have to build up first with the eigenvalue matrix. Then I need to just find the eigenvalues for them. In order to find the eigenvalues, I'm just going to go back from the previous sessions that we discussed and remind you of the concepts of the eigenvalues. Remember, we said that if we have the matrix A, the matrix A is multiplied, let's say, to the matrix X, then you see that you have these characteristics that the number is multiplied to the vector, let's say, X itself. In the previous sessions, you saw that we call the X, by definition, the eigenvectors and the lambda eigenvalues. This equation that we had over there, it plays a tremendous and a powerful formula in a variety of applications. Now, you remember what we did from the previous week was that I rearranged this. I said Ix minus lambda x becomes 0. Then the first thing that you just remember was that when you have something like this, you have to factorize x. Then what did we say was that? I said that the A minus lambda x equal to 0 matrix. However, A is a matrix, lambda is a number, X is a matrix, 0 is a 0 matrix. Then the problem that we had over there, you could not subtract the matrix from the number. Then that was the reason we introduced identity matrix, square matrix with the same ranking of the A, but everywhere it has a 0 components except the main diagonal. Then from there, we saw that we cannot have the X become 0, because what's the point? Because you remember previously you had alpha beta become 0. This gave you 2 logical reasons. The first was that the alpha is 0 or beta should be 0. This logic here becomes preposterous if x becomes 0, because we do not want the eigenvectors become 0. Then as a result, we are just going to move in with this one to say that, okay, then this one is 0. Then you saw that previously why we decided to have the determinants of A minus lambda I becomes 0. This was a thing that we discussed weeks ago. We called that characteristic equation of the eigenvalue determination. Now, it was a review of the things we did before. Now I'm just going to use this one to find the eigenvalues for this matrix. Okay, now I'm just going to move there. Okay, what is a deterministic equation? The determinant of matrix A minus lambda I should equal to 0. Let me rewrite my lambda like that. Lambda I should become to 0. The thing that we have over there is this. I have the given matrix A. Matrix A is given, which is 4, 2, the first column, 1, 3, the second column. It's mod minus lambda I. Lambda I. My matrix is 1, 0, 0, 1. I know that the determinant of this has to become 0. Now, in order to do so, the elementary things that we have from the matrices, you remember, this becomes the determinants then, because every corresponding element should be multiplied. Lambda, 4 minus lambda. On the first element, lambda times 0 becomes 0. Then 1 minus 0 becomes 1. 2 minus 0, because lambda 0 becomes 0 again. 2 minus 0 becomes 2. And lambda times 1 becomes lambda. Then you have 3 minus lambda. Becomes 0. Okay, now, the question is that now we just build the matrix like that. But look at this one. You have the determinant of this matrix. The determinant of the square matrix, we talked about that before. The determinant becomes the product of these two elements. I'm just going to write it here. Becomes, I'm going to write it there as long as I'm there. It becomes 4 minus lambda multiplies to 3 minus lambda, the product of this, minus the product of this. Minus 2 times 1 becomes 2, should equal to the right side, which I have the 0 there. Then, the thing which I'm going to do, I'm just going to expand this. 4 times 3 becomes 12. 4 times minus lambda, minus 4 lambda. Minus lambda times 3, minus 3 lambda. Minus lambda times minus lambda becomes lambda squared. And I have, do not forget, I have minus 2 over there. It equals to 0. Now, I'm just going to erase this part in order to solve it just right in front of the camera. Then you see that if you just rearrange the terms, you have the lambda squared, you have minus 7 lambda plus 10 gives you equal to 0. Okay, now this is the simplified format of the characteristic equation. The solution of this quadratic equation will give me definitely the eigenvalues. In order to do so, either you can solve it by the quadratic equation, or you're going to search for two numbers that their sum is, let's say, minus 7, or the product it becomes 10, which becomes 2 and 5, the roots. If you do not remember that things, I'm just going to solve it based on the quadratic equation. That the lambda becomes, if this is b, becomes minus 7, becomes plus 7, plus or minus, square root of b squared, 49, minus 4 times 10, 40, divided by 2. This is the way quadratic equation, delta method, in case if you do not remember those two methods, the method of common factors, which the answer is going to be 2 and 5, then you see that it becomes plus 7, it becomes 9, 3 divided by 2, you see that you have one answer. 7 plus 3 becomes 10, 10 divided by 2 becomes 5, then one of the answers is 5, the other one plus 7 minus 3 becomes 4, 4 divided by 2, then the lambda 2 becomes plus 2. Okay, now I got two eigenvalues from this equation. Then I got two eigenvalues. Very simply, I know that the matrix of the eigenvalues, which is the matrix, a diagonal matrix, is becoming this. Then I have two elements here, because that's a diagonal matrix. These ones are going to be 0. The eigenvalues show up in a descending order on the main diagonal. Descending order, it means that I'm just going to start with the biggest one, which this one becomes 5, this one becomes plus 2. Then that becomes the matrix, the dotted matrix, which represents the eigenvalues corresponding to the matrix A, which I have there. Now, the next step in our method, is to find the matrices of the eigenvectors. Now I'm just going to find the eigenvectors based on the eigenvalues which I find. Okay, but remember how to find the eigenvalues. Remember I said that, okay, we said that A minus lambda I times x should give me 0. This is good enough from the eigenvalues and eigenequation to find the eigenvectors. Okay, now A minus lambda I. I'm just going to start with lambda, which is equal, let's start with the 5. We said that if lambda is 5, what is going to be the eigenvectors for that associated with this eigenvalue? Then I say if that's the case, then I'm just going to start from there. I know what is the lambda. I know what is lambda. I know A, and it's going to be subtracted. I'm just going to multiply lambda to the I and subtract A. In that case, I'm just going to simply write it. It's going to be 4, 1, 2, 3, which is matrix A minus lambda, which is 5 times 1, 1, 0, 0. This is exactly this equation. When lambda is 5 and I is given and A is given, then what do I have? It becomes 4 minus 5 becomes minus 1. 1 minus 0 becomes 1. 2 minus 0 becomes 2. 3 minus 3 becomes 0. Look at that. 4 minus 5 becomes minus 1. It becomes 1. It becomes 2. And 4 minus 5, 3 minus 5 becomes minus 2. 3 minus 5, that's right, becomes minus 2. Let's double check further. I have 4 minus 5 becomes minus 1. 1 minus 0 becomes 0. 2 minus 0 becomes 2. 3 minus 5 becomes minus 2. This is this equation that I have there. I know that this one, I'm going to take this one over here. I know minus 1, 2, plus 1, minus 2 is going to be multiplied to the x, the eigenvectors. I'm just going to call that x1, x2, the elements of that, but the result is going to be a 0 matrix, which is 0 and 0. In order to find the x1 and x2, I'm just going to use the multiplication. I know that this is a 2 by 2 matrix. This is a 2. This is a 2 by 1 matrix. They are compatible for the multiplication. Then I have a 2 by 1 matrix, the resulting matrix which I get. Now, I'm just going to solve this by this one. I know that this one comes what? It's at the first row, first column gives you minus x1 plus x2 give me 0. This element which I have there is standing at the second row, first column. Then I multiply second row to the first column element wise. Then it becomes 2 x1 minus 2 x2 becomes 0. Then now all of these equations are the same. Then you can say that, okay, for example, you can choose this one. You see that in that case x1 should be called x2. Then, for example, the first eigenvectors that you can see from this, I'm calling v1, becomes x1 and x2 are equal, then becomes 1, 1, an arbitrary number n. Now, It was the first eigenvectors that defined. If you choose n equal to 1, you get eigenvectors 1 and 1. Now, the next thing which I'm going to do, I'm just going to choose a different value of the, let me erase this. Because I'm just going to do the exact same thing for the case that my lambda adopted the second value, which is 2, that the lambda becomes plus 2. If the lambda becomes 2, then I have 2 over here. Then let's see what's going to be the end result. I have 4 minus 2, I get 2. I have 1 minus 0, I get 1. I have 2 minus 0, I have 2. I have 3 minus 2, I have plus 1. Now, then as a result, this one becomes this is multiplied to x. I write 2 here. I write 2. I write 1. And I write plus 1. Now, in that case, you see what happens. We said that this element, which is 0, is at the row 1, column 1. Row 1 multiplies to column 1 becomes 2x1 plus x2 equals 0. The other one, 2x1, again, plus x2, give me 0. These equations are the same. I choose this one. Then you see that x1 equals to minus 1 over 2 x2. This is the thing that we get from there. You take the x2 to the other side, divide by 2, you get this expression. Then the second eigenvectors that we get is this. For the x, for example, I'm just going to choose, for example, for this, the case that we have over there, you see that for the x1, we have minus 1 over 2 x2. In that case, it means that if I have, for the x1, I have minus 1 over 2 over here, and the x2 becomes 1. Okay, this is going to be the second eigenvectors that we had over there. Or you can see that, you could see that, for example, if you choose this one, you get the same thing, that the x2 becomes minus 2x1. It was also another way to write the thing that we did over there. In that case, you see that x2, it becomes minus 2 over there. Then we had minus 2 over x1. Then you had 1. Let's choose with the second one, because it gives a more sense to what we did. For the x2, I'm just going to choose minus 2. And for the x1, I'm just going to use 1. Then I have n also. Then if I take n all to be equal 1, then you see that the eigenvectors that I'm just going to create is going to be this one. I'm just going to put this one. Plus 1, plus 1, plus 1, and minus 2. This is the vector of the eigenvectors for this equation which I had. Now, coming back to what we did, I'm just going to erase this part. Remember, for the eigenvalue decomposition, what we did was this. We said that, okay, a given matrix A can be decomposed into the matrix of its eigenvectors, the diagonal matrix of its eigenvalue, the inverse of its eigenvectors. That's what we discussed. Now, if that's the case, so far what we did, we find the diagonal matrix of the eigenvalue is this. We got the V, but the V inverse is also important. In order to find the V inverse, we can essentially write this. The V inverse, you remember it from the other courses that we had. The inverse of the matrix, which is diagonal, you have to multiply that to the inverse of its determinants, swap these numbers, and minus these two numbers to get this one. which in that case, you remember the inverse of a matrix. The criteria is that the matrix that you have over there is inversible if its determinant is non-zero. Let's find the determinants of the V. The determinants of the V, it becomes plus 1 times minus 2, becomes minus 2, minus these two, becomes minus 1, which becomes minus 3. As this is not equal to 0, then it means that the V is inversible. That the V inverse becomes, I'm just going to also write it, let's write it here. We said that the V inverse becomes 1 over the determinant minus 1 over 3. The vectors that you have over there, you swipe it this one, minus 2 plus 1, minus 1, minus 1. Then as a result, you got the V inverse, you got the V, and you got the matrix of, the diagonal matrix of the eigenvalues. And you see that then by having an arbitrary matrix, which we had A there, which was a 2 by 2 matrix, I was able to decompose that into by the method eigenvalue decomposition, by building the vectors matrix and the diagonal matrix, which represented the eigenvalues and the inverse of the eigen matrix that we had there. Okay, now this part becomes the second part of the course that we had today, which it was more practical aspects of one example on how to use eigenvalue decomposition.